Good day. We are presenting for today is all about sprinkler irrigation system. My name is Jover Asuncion. My member is Christian Antonio, Aris Bautista, Emerson Bautista, Eliza Beltran, Joseph Bermudez.
Overview. Design aspects, design principles, design steps or methodology, hydraulic design, example design. Introduction. Sprinkler irrigation is a method of applying irrigation water which is similar to natural rainfall. Water is distributed through a system of pipes, usually by pumping. It is then sprayed into the air through sprinklers so that it breaks up into small water drops which fall to the ground. Sprinkler irrigation is suited for rows, fields, and tree crops, and water can be sprayed over or under the crop cover. However, large sprinklers are not recommended for irrigation of delicate crops such as lettuce because the large water drops produced by the sprinklers may damage the crop. Sprinkler irrigation is adaptable to any farmable slope, whether uniform or undulating. The lateral pipes supplying water to the sprinklers should always be laid out along the land form whenever possible. This will minimize the pressure changes of the sprinklers and provide a uniform irrigation. Sprinklers are best suited to sandy soils with high infiltration rates, although they are adaptable to most soils. Sprinklers are not suitable for soils which easily form a crust. A sprinkler system must be designed to apply water so no runoff or erosion occurs. The application rate of the sprinkler system must be matched to the intake rate or the most restricted soil in the field. If the application rate exceeds the soil intake rate, the water will run off the field or relocate within the field, resulting in over and underwatered areas. Conservation, tillage, and residue management can help control runoff. These are the objectives. First is to determine different design of a sprinkler. Second, to determine how to compute and estimate the right size of sprinkler and pipes when designing sprinklers irrigation. To avoid crops and soil damage, using small diameter nozzles, operating and using the normal recommended operating pressure. These are the advantages. First is the expansive land leveling is not required. Water-saving irrigation intensity can be changed in accordance with the infiltration capacity of soil. High efficiency due to uniform water distribution. No special skills trained personnel can operate the system reasonably well. Is an uniform application of fertilizers and pesticides true. Probability of applying minute, quantity of water for germination and other irrigation system. Frequent and light irrigation possible, giving response from the crops. Increase in yield and quality. Early ripening, water conservation, and alternative value of a specific period, saving of labor, machinery, fertilizer, and pesticides. Soil moisture is maintained at optimum level by sprinkler irrigation, and 20 higher yields are obtained of crops, and the quality of other crops is also good. Disadvantages: higher initial cost, high and continuous energy requirement for operation under high wind condition and high temperature distribution, and application efficiency is poor. Highly saline water, 7 mm Hg per centimeter, causes leaf burning when temperature higher than 95 Fahrenheit. When lands have been already leveled and developed for surface or other irrigation methods, sprinkler irrigation is not so economical. Loss of water due to evaporation from the area during irrigation. Above canopy, sprinkler may cause washing of spray materials and aggravate the incidence of pests and diseases.
Design aspects of sprinkler irrigation system. Sprinkler systems have revolutionized the development of irrigated agriculture. Efficient water application with sprinkler irrigation involves the design and operation of pumps, pipes, and sprinkler devices to match soil, crop, and resource conditions. Thus, sprinkler systems can be designed and operated for efficient irrigation for a wide array of conditions. Sprinkler irrigation also facilitated the expansion of irrigated agriculture onto lands classified as unsuitable for surface irrigation. Initially, the labor required to transport the system across the field impeded the adoption of sprinkler irrigation. Through automation, the labor required for sprinkler irrigation has been reduced significantly. Reduced labor requirements enable producers to irrigate more frequently with smaller water applications, which diminish unintentional leaching and increase the potential to store precipitation in the crop root zone while satisfying crop requirements. Components of sprinkler systems. Sprinkler irrigation system generally consists of a pump used to lift and pressurize water, a mainline piping system to convey water from the pump to the lateral pipelines used to transport water across irrigated field, and sprinkler devices to apply the water within the field. In some cases, the main line is subdivided into submains to convey water to portions of the field. Multiple laterals may be used if the field is large or if the field needs to be irrigated frequently. Sprinkler devices are installed at intervals along the laterals. Often, a pipe called a riser is used to adjust the height of the sprinkler device to the desired height to avoid crop interference with the jet of water discharge. For some applications with center pivot or lateral move systems, The sprinkler device is suspended below the lateral using drop tubes to minimize evaporation and drift of sprinkler droplets. The proper spacing of sprinklers along the lateral is crucial to providing enough overlap of water from adjacent sprinklers to achieve uniform irrigation. Laterals can be periodically moved from one location, often called a set, to the next location as with hand move systems, or the laterals can move continuously across the field as with center pivot and lateral move systems. When the sprinkler lateral is periodically moved across the field, the distance between subsequent sets of the lateral must be narrow enough to provide for adequate overlap. Many kinds of sprinkler devices are available. All sprinkler devices use a nozzle to control the discharge from the sprinkler. The diameter and shape of the nozzle orifice and the water pressure at the nozzle control the rate of flow. The nozzle converts pressure within the piping system to velocity upon discharge from the sprinkler. The velocity propels droplets through the air to provide a wetted pattern about the sprinkler. The design of the nozzle and the sprinkler device determines the diameter of coverage and the distribution of water within the wetted region as with any irrigation system. The sprinkler system must be laid out to conform to the boundaries of the field. The dimensions of the field physically or economically often dictate the type of sprinkler system to be used. Ultimately, the components of the sprinkler system must be matched to irrigate efficiently and economically. Inappropriate specification of any component will negatively affect the entire system. Sprinkler layout. These are the components: water source, pump, delivery pipe, bypass valve, screen filter, pressure gauge, QRC pump connector, sprinkler metal nozzle or sprinkler plastic nozzle, control valve, QRC-T, QRC end cup, riser pipe, QRC bend, QRC service saddle, and example of crop. Wetting patterns in sprinklers. The wetting pattern from a single rotary sprinkler is not very uniform. Normally, the area wetted is circular. The heaviest wetting is close to the sprinkler. For good uniformity, several sprinklers must be operated close together so that their patterns overlap. For good uniformity, the overlap should be at least 65% of the wetted diameter. This determines the maximum spacing between sprinklers. Wetting pattern for a single sprinkler, which is the top view. The wetted diameter, which is the broken circle as we can see in the figure, and the lateral and sprinkler. The wetting pattern for a single sprinkler, which is the side view. We can see the lateral and sprinkler and the wetted area of the land. The uniformity of sprinkler applications can be affected by wind and water pressure. Spray from sprinklers is easily blown about by even a gentle breeze, and this can seriously reduce uniformity. To reduce the effects of wind, and sprinklers can be positioned more closely together. Sprinklers will only work well at the right operating pressure and recommended by the manufacturer. Peak crop water requirements during the growing season. Maximum effective crop root depth, texture, and infiltration rate of the soil, available water holding capacity of the soil, pumping capacity of the well or wells, State Water Commission permitted pumping rate. Table 1 shows the system capacity in gallons per minute per acre for different soil texture needed to supply sufficient water for each crop in 9 out of 10 years. An application efficiency of 80% and a 50% depletion of available soil water were used for calculations. Examples of crops are potatoes, dry beans, soybeans, corn, sugar beets, small grains, and alfalfa. And it is calculated for root zone depth, coarse sand and gravel, sand, loamy sand, sandy loam, fine sandy loam, loam and silt loam. For example, if you plan a 3-year rotation of potatoes, corn, and soybeans on loamy sand, you can determine from Table 1 that potatoes require 7 GPM per acre, corn with 5 GPM per acre, and soybeans with 6.4 GPM per acre. Select a design system capacity for the potatoes at 7 GPM per acre. If you install a center pivot system covering 130 acres, ideally you would need about 910 GPM or 7 by 130. The most common irrigated soils are loamy sands or sandy loams that require a flow rate of about 6 GPM per acre for full season irrigation. A lesser flow rate can be used, but more intensive water management will be required, especially during years with less than average growing season precipitation.
Design procedures. Main components of a sprinkler system are: first, pumping station. If required in a gravity flow system, no pump is needed. Mainline pipe, lateral pipe, riser, and sprinkler. The pumping station is located at the water source, and the pump lifts the water and makes it available under pressure to the system. The pump is required to overcome elevational differences between the water source and the field, counteract frictional losses within the system, and provide adequate pressure at the nozzle for good water distribution. The main line delivers water from the water source to the field. It may be either permanent or movable. The lateral pipe delivers the water from the main line to different sections of the field. The lateral line is usually movable. The riser delivers the water from the lateral line to the sprinkler. The length of riser depends on the crops, although a minimum value of 30 cm is required. The sprinkler is the unit that sprays the pressurized water through an orifice and rotates to distribute water onto the field. The accessories are parts of the system that generally connect all of the other units together to form a watertight system. These parts are very important to an efficient system and should be installed whenever. Fine specifications. Type of materials are galvanized steel, aluminum, polyvinyl chloride, polyethylene, and soft plastic. Sprinkler heads and nozzle types of materials. So these are the materials: metal, plastic, combination metal, and plastic. So types of sprinkler, 1, 2, 3. So there are 3 types of sprinkler. The first one is microjets. A mist type sprinkler used primarily in seedbeds and underneath foliage of certain crops. Second is one nozzle sprinkler. Components include hammer range nozzle. Third is two nozzle sprinkler. Components include hammer range nozzle and spreader nozzle. And these are the image of hand move sprinkler system using two laterals. And the circle are the distance of water and so forth. A solid set permanent laterals. This sprinkler irrigation system is similar to the portable system except both main lines and laterals are generally buried below the depth of normal field operations. Sprinkler lateral flow can be sequenced manually or automatically by various timer-activated electric solenoid valve with annual crops. The risers are installed outside of any tillage operations. This system is most adapted to permanent crops such as orchards, grapes, cranberries, caneberries, turf for landscaping, and golf courses. Solid set system can be used on annual crops, alfalfa, or pasture. However, caution must be exercised during tillage or harvest operations to prevent damage to risers and sprinkler heads. Risers must also be protected from livestock.
If the pressure is above or below this, then the distribution will be affected. The most common problem is when the pressure is too low. This happens when pumps and pipes wear. Friction increases and so pressure at the sprinkler reduces. The result is that the water jet does not break up and all the water tends to fall in one area towards the outside of the wetted circle. If the pressure is too high, then the distribution will also be poor. A fine spray develops which falls close to the sprinkler. Application rate. This is the average rate at which water is sprayed onto the crops and is measured in millimeter per hour. The application rate depends on the size of the sprinkler nozzles, the operating pressure, and the distance between sprinklers. When selecting a sprinkler system, it is important to make sure that the average application rate is less than the basic infiltration rate of the soil. In this way, all the water applied will be readily absorbed by the soil and there should be no runoff. Sprinkler drop sizes. As water sprays from a sprinkler, it breaks up into small drops between 0.5 and 4 millimeter in size. The small drops fall close to the sprinkler whereas the larger ones fall close to the edge of the wetted circle. Large drops can damage delicate crops and soils, and so in such conditions it is best to use the smaller sprinklers. Drop size is also controlled by pressure and nozzle size. When the pressure is low, drops tend to be much larger as the water jet does not break up easily. So to avoid crop and soil damage, use small diameter nozzles operating at or above. Sprinkler system capacity. The sprinkler system capacity is the flow rate needed to irrigate an area adequately and is expressed in gallons per minute per acre. The required irrigation system capacity is dependent on the
Sprinkler irrigation system design. This guide is generally approach on how to design and install a home landscape irrigation system. The step would be much the same for most any irrigation system. We gathered the We tackle the gathered information, design the layout, select the materials, install the system. Step 1. Gathered information. Decide whether you want an annual or automatic system. The process would be the same except that a controller, automatic valves, and wire are necessary to operate an automatically controlled lead system. We recommend if it is a large or complex system, you should get the help of a certified irrigation designer or a qualified landscape architect. Find out the following information. Letter A. Static water pressure. If you have city water, call your local water department or use pressure gauge on garden bulb output nearest area to be watered. No water should be running in or around the hose. B. Water meter. Check the meter or call the local water department. And C. Gallon per minute. Of course, to measure the gallon per minute. And plumbing regulation building permits needed. Call the city hall or the local building department to that regulation. Inside diameter or of pipe service line running from water meter or pump to hose. Wrap a piece of string around the outside of the service line. Measure the length of string required to encircle. And F. Determine backflow prevention device requirements of city or water system. That is the outside faucet and pressure gauge. And this is the for finding pipe diameter using a string in the above and the below the backflow preventer selection criteria. We have continuous pressure, possible back pressure, low hazard, high hazard, and so on and so forth. In step 2, plan your system. Use a planning grid to make an accurate scale layout of your property. A. Include location of house, driveways, walkways, paths, fences, walls, structures, planters, patios, flower beds, shrubbery, and lawn areas. See in diagram 1. Shade in all area to be covered by water lows, shrubbery, special ground, etc. Indicate water supply location, spigots, well, water service entrance, etc. Use PVC or polypipe. PVC is like glue type joints and polypipe is a flexible hose type. Step 3. In step 3, select and position sprinkle heads. Select and position your sprinkle heads. It identifies the major types of standard heads, gives their uses and gallons per minute or GPM, tells what patterns are available and suggests correct spacing requirements. This is a general chart. For more specific information, check the manufacturer's performance chart. This is the production guide. We have spray, heads, shrub, adapters, pop-ups, gear-driven rotary, sprinkler, impact sprinklers, plastic, and brass. Where the uses, spacing range, distance of throw, average of GPM at 30 psi. For step 4, determine size, number, type, and location of bulbs. Begin grabbing large lawns areas. Place quarter circle heads in the corners. Place half circle heads between corners, following recommended equal distance spacing. Refer to product guide. Place full circle heads within each perimeter. The number will depend on the perimeter's overall dimension. Now position heads in small lawns areas, parkways, and at the side of your house. These areas are usually watered by one or two rows of part circle heads. As you can see the diagram, the point of the pointed of the diagram is the sprinkler, and the range of the water is the in the circle, just like that. Complete grabbing of heads by positioning them in flower bed, shrubbery areas, planters, and other special places. See diagram 4. Shrub head pattern or equivalent to regular head pattern. For good coverage, you want to have 100% overlap of heads. For step 4, determine the sizes, number, type, and location of control bulbs. A. Bulb sizes are determined by the size of your water meter and size of your service line. Your bulb sizes do not need to exceed your service line size. And B. The type of bulb depends on local plumbing regulations. Most cities require an anti-siphon control bulb to prevent dirt and foreign matter from draining back into the main water system. And C. Bulb location are determined largely by their nearness to your service line and existing outlets. Pick a convenient location away from heavy foot traffic. Group your bulbs together to save on supply line pipe and other materials. Step 5. To determine size of supply line. The supply line is the piping from your water source, such as your water meter or well. The line servicing the dwelling or the existing outline to the sprinkler bulbs. And D. Because of friction loss in the supply line, it is necessary to consider the distance from the connection to the bulb location. C. Determine the type of pipe you wish to use. Of course, uh, kahit anong gamitin mong gamitin mong pipe na pwede dun sa sprinkle ay pwede mong ikabit. And D, once the pipe is selected, draw lines on the plot plan connection, the sprinkler in each zone to each zone bulb. This is the chart. Maximum flow in gallons per minute. We have pipe size, PVC class 200, PVC schedule 40 and 45. For step 6, group sprinklers and graph plan. A. Sprinkler group is the number of sprinkler head adjacent to each other that will work of the same control bulb. If at all possible, all sprinkler in a group should be of the same function. For example, only bubbler should be grouped together starts at the end of each particular sprinkler. Group and work towards its control bulb. Noting the number of plant heads. If you have 3 bulbs, you will have 3 groups of sprinkle. And B. Determine the number of circuits needed. This flow rate depends on 3 factors: the service line size, the static water pressure, and the type of sprinkler used. And C. Starts at the control bulb and layout the piping system. Draw a feed line through the middle of each sprinkler group. Draw in inside branches to adjacent head. For example, to determine the GPM, chart indicate that with 3-port supply line and 40 psi, You have 9 gallons per minute available. In step 7, set the controls. Layout of the piping. In your system, piping will run from the service line source of water to the first set of bulbs, then from the first set of bulbs to the second set, and from the bulbs to the sprinkle heads. Disconnecting pipes on your grid layout and follow these rules. Use as many straight runs as possible. Avoid turns which result in friction and loss of pressure. Avoid going under sidewalks and driveways whenever possible. As you can see the picture, for the right or the incorrect is to avoid forcing water through the many turns. But in the correct or the for the left, the design connection pipe is that several lines branch from the first head in the circuit. For step 8, set your control bulb setting your control bulbs. A. To connect the supply line shut off water at the meter, cut a section of the service line and insert a standard slip coupling T. Run the supply line to the location of your bulbs. To connect to an existing garden hose outlet, simply remove the bulb and insert a nipple and a T. Replace the hose bulb and run pipe down to the sprinkle bulbs. As you can see the diagram, we have the garden bulb, T, supply line, elbow, straight bulb, bulb sleeve, elbows, anti-siphon bulb. And the other is we have elbow, T's, and on. P is a group of bulb is called a manifold. In a manifold, use fittings and pipe the same size as your bulbs. And C, install your bulbs making certain that antiphon bulbs are 6 above the ground and 5 apart to allow for an adapter to automate the system at a later date. Angle bulbs should be buried. Refer again the diagram 5 for typically bulb installation for a single bulb or refer to manifold bulb hookup. And D. Do not install anti-siphon bulbs under constant pressure para iwas masira. In step 9, positioning your sprinkle heads. Using stakes and strings, mark the location of your heads and piping. Important maximum GPM flow may vary significantly because of pressure losses resulting from size and type of pipe use as well as total length of pipe in an installation. Another information factor is elevation because you will lose approximately 1/2 psi per foot of elevation going up a hill and gain approximately 1.5 psi per foot of elevation going down a hill. Therefore, before backfilling any trenches, hook up each circuit and test for sufficient coverage. B. Dig trenches 5 to 6 step, putting any sod on one side and any dirt or soil on the other side of the trench. Just for cold climates, lay the pipe so the water will flow. Hard ground should be watered 2 days before trenching. And C. Locate bulbs. Bulbs can be located above ground or to keep them out of sight. Below ground, use stakes to mark the location of the bulbs as indicated on your grid diagram. Protect bulbs by sheltering them in boxes. You can buy boxes or build them yourself, of course. After hooking up, close all the control valves on your manifold and open the master valves. Check all connection or leak. For step 10, connecting your pipes. After all trenching is finished, connect all threaded fittings first, starting at the water source. Then connect all slip or insert fittings. If using galvanized pipe, use an adequate amount of pipe joint compound. If using plastic pipe, be certain of a leak-proof seal. B. How to cut and connect PVC pipe. Cut PVC pipe to desired length with a hacksaw or PVC cutter. Wipe, cut clean, and remove burrs. Second, apply solvent and glue to both pipe and fitting. Push pipe as far as possible into fitting. Make 1/2 turn for sure sealing. Wipe off excess solvent and glue. As you can see the picture, the elbows ay nilalagyan ng solvent or glue to avoid leak the water. And see, locate valves can be located above ground or to keep them out of sight below ground. Use a stake to mark the location of the valve as indicated on your grid diagram. After hooking up, close all the control valves on your manifold and open the master valve. Check all connection for leaks to assure that no leaks in your activities. For the step 11, flush system. A flush, si- a flush the main line. Wait for the solvent to dry about 1 hour. Close all valves except the one at the end of the line. Turn on the water flush until the water runs clear. Shut off the last valve and check for leaks. For B, flush the valves. This removes any dirt or soil that may have gotten trapped in the valves during the installation. Install the automatic system timer. Locate the timer in your garage or some other convenience place. Make sure an adequate power supply is available. Flush the system. Seal risers with pipe plugs. Leave the risers at the end of the line unplugged. Turn on the water, open the valves, and flush until the water runs clear. Remove the pipe plugs. For, for the last step, check system operation. Turn on the water and open the control valve if coverage is complete. Make sure the control valve, main valve, and shut-off valve are open all the way. Turns off any water being used in the house, washers, showers, sinks. Adjust the screw on the sprinkle heads to fine-tune the spray pattern. If coverage is still not complete, go back and check your system layout against the plans. When coverage is satisfactory, fill in the trench with dirt and cover it with salt. You've just installed a working circuit to finish the job. Repeat this step for all circuits in the system. And just relax and install the system one circuit at a time. And for the hints on operation, operating your system, operate only one valve at a time. This is a tips only. Water when pressure will be the greatest. This will probably be early in the morning. Water sharp trees and plants deep and less frequently. And water low areas for shorter periods and more frequently. And do not water in the heat of the day to cut down on water evaporation. This will also eliminate the burning of plant and down areas. Sprinklers should be cleaned periodically to ensure proper functioning. And that is my presentation.
Hydraulic design of a sprinkler system. So, discharge of a sprinkler na ba yung discharge? Discharge, it is the volume flowing in a unit time, which is sa nozzle, Q is equal to C times AC times 2GH divided by 2, where Q is the discharge in cubic meter per second, in square meter due to gravity, which is a constant value of 9.8 meter per second, and H is the pressure head. C, coefficient of discharge, which is ranging from 0.95 to 0.96 for good nozzle. Water spread area of a sprinkler. So from this formula, from Kawasa formula for rotating head sprinklers, the radius is equal to 1.35 times the diameter of the nozzle times the pressure head of the nozzle divided by 2. So that is the radius of the rotating head sprinkler. Maximum coverage attained when jet emerges at an angle of 30 to 32 degrees from horizontal. So if the angle of the jet is 30 to 32 from the horizontal line, the maximum coverage will be attained. Breakup jet. Breakup jet, it is the accessories in a sprinkler which is breaking up the water, and it will turn to a drop size to make the wetting front of the soil become appropriate. So index of jet break up by Tanda formula, PD is equal to H divided by 10Q raised to 0.4, where if the PD is greater than 2, drop size is good. If the PD is equal to 4, drop size is best. If the PD is greater than 4, pressure is being wasted. So water application rate, A is equal to the discharge or rate of application divided by 360 AW, where A is the water application rate in centimeter per hour. AW is the wetted area, the wetted area of a sprinkler, and it should be in square meter, where Q is the rate of application, which is in liter per second. Design of a sprinkler main, submains, and lateral. So as you can see in the figure, HN, which is in this left side, it is the head at the main line. HA is the average head. HO, pressure at the farthest. E is the maximum difference in elevation between the purse and the sprinkler on the lateral. So as you can see here, the lateral and the purse sprinkler and the last, their difference is the HE. So HR is the riser height, which is the height of the first sprinkler in the lateral line. HF is the friction head loss. So average head, HA for the design on the sprinkler line, HA is equal to HO plus 1/4 HF. So as you can see in the figure, HA, to get the value of HA, so HA is equal to the HO, as you can see, and the 3/4 or 1/4 HF. So value of HA, so HA is equal to the HO, as you can see, and the 3/4 or 1/4 HF. So HA is equal to, if the lateral is on nearly level line, N is equal to HO plus HF. So if the design is in a leveled surface or in a flat surface, the HN will be equal to the HO plus the HF, friction head loss. By solving for HO and substituting in HN equation and making allowance for differences in elevation along the lateral, HN will be HA plus the 3/4 of HF plus 3/4 of HE plus HR. As you can see in the figure, HN is equal to the HA plus the 3/4 of HE plus the 3/4 of HF plus the riser height. So mainline pipe size. Function of mainline and submains is to convey the required quantity of the water at the desired pressure to all lateral lines under maximum pressure condition. So the allowable HF in mainline is 3 meter for small systems and 12 meter for large systems. Friction loss for different pipe materials is estimated by this formula. HF is equal to K times C times L times QM times F divided by T2M minus N, wherein the M and N and K value is here in the table. So same formula in estimating the friction loss, but the value of M and N and K is not equal. So the L there is the length of a pipe, and K is the friction factor, depends on the material. Q is the flow rate, and F is the friction factor, or equal to 1 if there is no outlet. F can be determined as follows. When the distance from pipeline to the first pipeline equals to the outlet spacing, this is the formula that we should use. It said that when the distance from the pipeline or the distance of every sprinkler is equal, determine the friction loss, we will use it formula. The next is when the distance to the first outlet is half of the outlet spacing, it will be the formula to be used. So when the sprinkler or outlet spacing is half of the first sprinkler or outlet spacing is half of the first distance of outlet, this formula we should use, where N is the number of sprinkler and E there is the summation pumps and power unit. So the pumps and power unit, we matedetermine natin siya sa pamamagitan pag nalaman na natin yung total design head. HT is equal to HN plus HM plus HJ plus HS, where HT is the total design head in meter, HN is the max head required at the main to operate the sprinkler in the lateral, which average HM is the max friction loss in the main suction and line. So HM is the head loss from the suction to the main line. HJ is the elevation difference between the pump and the junction of the main and lateral. HS is the suction head, or the elevation difference between the water source and the pump. So when we already determined the total head, we will now going to determine the power of the machine or the pump that we are going to use. So power is equal to HT times Q divided by 75. 75 is a conversion factor, so the power should be in HP. HT is in meter, Q is in liter per second. So here, this source MS Nosil Akola Mahastra, design specifications of sprinkler with different nozzle size and operating pressure for high pressure model HP. So in this source, we determine the nozzle we are going to use, and their discharge, and the spacing of every outlet or sprinkler, and the spacing of the lateral line. We will determine that here on the MS nozzle Akola chart. So thank you.